second lecture on error correcting codes, and let me just bring you to the title of our lecture today. So, our lecture today is entitled Error Correcting Example Codes and Their Parameters. But normally what I do is before I start every lecture, I give an overview of what we have covered in the previous lecture, and I will also do that today. But there was this other thing that I actually wanted to do, which was to show you some of the textbooks that you might want to take a look at just to get just to use them as a reference. So, let me just quickly do that, then I will come back, I will summarize the last lecture, and then we will continue with our lecture. So, here now these textbooks, I must say, are not in any particular order. So, it's a random order. So, there is one book, Stephen Wicker, Error Control Systems for Digital Communication and Storage. This is 1995, so not quite the latest textbook, but still not bad. So, this is one of the textbooks. It's a well written textbook. It's quite balanced, a little on the older side. To the right is a textbook which is dates back even further, back to 1981. But one of the things that I particularly liked about this textbook is that it is extremely well written, and it's easy to read. The authors avoid formulae or equations wherever possible, and yet convey much of the meaning. But of course, since it is 1981, this is clearly dated, but still it is also written from a rather practical point of view, because these authors are actually practicing engineers. So, it is a little bit different, because most of the other textbooks are written by people who are professors in some university or the other. This one by contrast is this one on the left over here, is this one here is a more recent textbook, The Fundamentals of Error Correcting Codes by Huffman and Vera Pless. It is 2003, very well written. These same authors actually put together a handbook on coding theory, which is about several thousand pages long, and they got contributions from the leading coding theorists around the world. But then subsequently they brought out their own book, and this book is very well written, very carefully written. I think to some extent the textbooks differ in their coverage of the topics. For example, one author who has done research in a particular topic might actually emphasize that topic in relation to the others. Okay, so that often is the difference between textbooks. Now, the other comment I guess I should make is versus this issue of the classical coding theory, which tends to be algebraic, versus the modern, which tends to be probabilistic. From that point of view, this book, for example, this book is algebraic. It does not consider the modern coding theory viewpoint, simply because it was written a little before modern coding theory took its current place. Similarly, the same is true of this book, except that it is written, as I just explained, in a not so mathematical manner. This one, it does try to include some of the modern coding theory, but really the authors are experts in algebra and combinatorics, and the book reflects that. Similarly, here if you look at Ron Roth, he is a classical coding theorist, although he does cover some of the modern aspects as well. But again, you can actually, as you browse through the contents of this book, you will see that the author's personal research preferences show up in terms of the emphasis on different topics. Now, first let me begin with this book on the right. This book on the right was the classic. It was it's a 1977 book, so very much dated, but in its time it was considered a Bible. It's the Bible from an algebraic coding theory point of view. It's like an encyclopedia. Anything that you wanted could actually be found there. It's beautifully written, but very compact. Okay, so every word, there is no extra word in this entire textbook. Okay, but also it is restricted to the algebraic coding theory viewpoint, and even there, for example, it does not treat the topic of convolutional codes. Okay, Okay, so it is rather specialized, but given that it is a superb textbook. On the left you have kind of the opposite model, which is the modern coding theory textbook. I think it is a year or two old, and it is completely different from all the other textbooks because it takes predominantly the modern coding theory viewpoint, which is that it is very probabilistic, and it emphasizes low density parity check codes or turbo codes and so on. Very nicely written. The authors are very are experts in this area. The textbook on the left here, maybe I will just magnify this a little bit. This textbook on the left here, Error Control Coding by Shulin and Dan Costello, this was the default reference textbook for many years, and basically because all topics were covered, and the two authors were experts respectively in block coding and convolutional coding, and so it made for a balance. Now that with regard to modern coding theory, the authors have done some work in this area, particularly the first author. So, they do pay some attention to that as well in their topic. So, basically what they have done is they have taken their textbook and then they have upgraded it to include the modern coding theory viewpoint. Okay. It's for many people will actually like, if you had to use a single textbook, you might actually think of considering this book. To the right is a book actually on optical fiber telecommunications, as you can see here. So, you might say, well, what is an optical fiber telecommunications textbook doing here? Well, as I mentioned last time, that in this handbook published in 2002, a bunch of us had occasion to write a chapter on error control coding techniques, and my discussion of the topics will be in the same sequence as is covered in the chapter. Okay. So, this might be another useful reference for you. Okay. So, there are 8 textbooks here, but in reality, but if you look out in the market, there are lots of books on coding theory. Many textbooks have come out in the recent few years. So, this is by no means exhaustive, but just to give you an idea of some of the textbooks that you are likely to encounter. Okay. So, with that I will close on this, and then we will move on to talking about the lecture. Lecture 2 is example codes and their performance. So, let us quickly preview the previous lecture. Just for an overview purpose, I think that this level of magnification should suffice. What I did last time was basically said I am going to introduce the course in terms of a flow chart. So, here what you see here is like a flow chart. So, I discuss over here in the second slide. Let us see if you can see this arrow. Yes, there you go. So, on this side what I do is I discuss in this slide, I tell you how we are going to start off the course by talking about basics of binary codes, then we will move on to linear binary codes, and then as a side topic we will consider the topic of convolutional codes. Then after convolutional codes, we will move on to the modern viewpoint, which is which as I said is probabilistic, but we will approach it from the point of view of an algorithm that is very efficient in terms of minimizing computation, and that algorithm has its basis in something called the generalized distributive law. So, we will cover that. We will spend 3-4 lectures on it, and then go on to talking about the modern codes, which are examples of which are low density parity check codes and then turbo codes. And after that, at the end, we will actually start talking about the algebraic viewpoint, which will begin with finite fields and then go on to talking about specific classes of codes which make use of the algebraic viewpoint. Then the next thing that I did was to actually talk. So, maybe I can actually zoom out a little bit. Yeah. So, that was the first part. Then the next thing that I went on to do is to consider to discuss discuss channel models here, and the particular channel model that we will be dealing with for the first few lectures is the so called binary symmetric channel model. And what I did there was I explained how a second channel called the additive white Gaussian noise channel, and which perhaps is closer to what you might imagine a channel looks like, how that an approximation of that leads to the binary symmetric channel. The binary symmetric channel is the one that we will focus on. So, the input is both binary, the input and output are both binary. So, that leads to the question, how do you do arithmetic working with just the binary set 0 and 1. So, we talk about addition and multiplication and how these are carried out when your set is 0 1, and then we actually say how do you extend it for the case when you have vectors where the symbols individually come from 0 and 1. Then we introduce some terminology, we introduce what is meant by the Hamming weight. The Hamming weight of a vector is the number of non-zero components in the vector. So, here you see the space of vectors where the symbols come from F2. I give you an example, and the Hamming weight is the number of non-zero components, and the Hamming weight function has certain properties which we actually discussed, and this led naturally to discussion of the Hamming distance between two vectors, all right. And we define the Hamming distance as simply the Hamming weight of the sum vector, and again there are some properties, one of them being the triangle inequality, which corresponds to this figure. After that I said, okay, I think we are now have the setup where I can actually tell you what in a very general way a binary block code is. So, a binary block code is simply any subset of the set of all n tuples, and here what we see in this figure is a collection of n tuples, and certain selected ones amongst these correspond to the code words, and array correction takes place because given that you transmitted a code word and given that the channel has perturbed that code word to another vector that is close by, you can often correct for that error simply by saying, well, this was transmitted, this was received, but since this is closest to this, most likely that was transmitted. So, you guess what the transmitted code word, and that is how error correction takes place. And then I started talking about the parameters, the different parameters of a block code. One is of course the size, which in some sense measures how much information. So, one parameter of course is the size of a code, which is simply a count of the number of code words in the code. The second is the rate of the code. The rate of the code, if you take an information theory, is a measure of how much information you are sending along with the code word per channel use. If the code word has length n, then in reality what you are doing is you are using up n channel uses. So, the amount of information when you average it over per channel use, it turns out from an information theoretic point of view, and the units in this case are bits per channel use, bit being a very clearly defined quantity in information theory. So, it is log of the size of the code to base 2 divided by n, that is the number of bits per channel use that you are transmitting. Okay. So, the bigger the code, the more the information that you are sending, and the third then there is of course the block length of the code itself, which is just simply the number of components in each vector, and then there is the minimum Hamming distance. The minimum Hamming distance is really a measure which tells you how close do two code words come together, because the smaller the distance, the lesser the error correction capability of the code. So, what that tells us is that building an error correction code is really all about trying to actually within the set of all n tuples picking certain vectors as code words, and the number of them is a function of how much information you want to actually convey, but how much error correction capability you get is really dependent upon how well spaced these vectors are in the space. Okay. All right. So, having introduced the parameters, so what we will do today, and that is the title of our talk, is we will look at some example codes and their parameters. Now, typically what I do is I ask questions in the class and then I say, does anybody know of an error correcting code, and usually we do get responses, and the most common responses are very good examples to begin this theory with. So, I will actually start with those. So, the first example that you might actually think of is the repetition code. Now, all of our example codes will have block length 7. So, let me make a note on the side of on that. So, the repetition code in this case will just simply consist of two code words, the code word being the all 0 code vector as well as the all 1 code vector. Okay. Now, let us go about seeing what the parameters of this code might be. So, the size of the code is of course 2. The rate of the code is, remember, it is log to base 2 of the size of the code divided by n. So, in this case that would be 1 by 7. The third parameter is the block length, but I have already pointed out that all of our example codes will have block length n equal to 7. So, the last parameter is the minimum distance of the code. So, the last parameter is the minimum distance of the code, that is what is the minimum spacing between a pair of code words in the code, distinct code words in the code, and you can see in this case that the minimum distance is 7, right. So, this of course, since your vectors have length 7, I am sorry, there is one typo here. This 0 should have been a 1, let me just quickly correct that. Yeah. So, there are in this case the code size is small, but the separation is large. In fact, the separation is as large as can be. Let us go on to our next example. So, example 2 is the so called single parity check code, and we will abbreviate this as SPC code, single parity check code. And the way you define this is that C is the set of all vectors of the form under the constraint that summation is equal to 0. Now, just a reminder here, and I will not discuss this too many times, but whenever we talk about any arithmetic, we will always mean modulo 2 arithmetic. So, for example, when I write down the condition that the sum of the symbols must be 0, what you mean is that the sum after it is computed modulo 2. So, the modulo 2 sum is equal to 0 is the way you should actually interpret this, okay. But I will not mention that in the sequel, we will always assume that to be the case. Now, again with regard to code parameters, you have that the size of the code is 2 to the 6, and that is not hard to see, because after all you can choose the first 6 components arbitrarily, and the 7th symbol gets fixed by the parity constraint. The block length of course is 7, we have chosen that. The rate of the code is, we are going to take the log of the code size to base 2, divide by 7. So, that will be 6 by 7, and then that brings us to the minimum distance of the code. The minimum distance of the code is the minimum distance between a pair of code words, and if you think about it, another way you can actually try to answer the question as to what the minimum distance of a code might be is just to ask yourself the question, if let us say that x1 through x7 is a code word, then how many of these symbols must I flip in order to get a second code word? And it is not actually hard to see that if you flip one symbol, then the parity condition will be violated, and therefore no two code words can be one symbol, can have a Hamming distance of 1. They cannot differ in just one symbol, but you can certainly flip two symbols and satisfy the even parity constraint. Thus, the minimum distance of the code is actually equal to 2 in this case. And if you want a small example of that, you can, it is not at all hard to construct. For example, you can consider the Hamming distance between the vector of all zeros and the vector whose first two components are 1 and the remaining components are all 0. So, the Hamming distance is 2, and in both cases I know that they are code words, because after all the parity check constraint is actually satisfied, right. So, that is our second example. Now, let us look at our third example. The third example will be the Hamming code. It turns out that the Hamming code is really a chain of error correcting codes, and these codes can have different lengths. They are always of the form 2 to some power minus 1. Okay. So, now we are looking at the code whose length is 2 to the 3 minus 1. There are you can present the Hamming code in a number of ways. Some years back I listened to a seminar by a well known coding theorist, Bob McLeish, and he presented it from a rather interesting point of view, and he was saying, you know, I can explain the Hamming code to a 5-year-old, and we were skeptical at first, but as he gave the lecture it became clear, yes, of course you can do that. Okay. So, I am going to present that viewpoint to you, and afterwards we will view it from a different perspective, which will allow us to generalize it to a larger class of codes. Okay. I myself presented this viewpoint to some children who were 5th graders, so not quite 5-year-old, they were 10 years old, and they seemed to understand perfectly well. I am going to put down some symbols, and I actually I called it the magic of 3 circles when I actually presented it to them. So, let me just introduce some notation. So, M0, M1, M2, M3. Okay. So, each of these represents a symbol, and it turns out that in the Hamming code that you can pick these symbols any way you like, but of course this is a binary code, so you can only make it either 0 or actually 1, right. So, there are only 2 possibilities. So, that means the total number of code words is therefore 2 times 2 times 2 times 2, which is 16. So, the Hamming code will actually contain 16 code words. Let us go about seeing how, after all, the code has block length 7, that means there are 3 more symbols to this code word. Let us go about introducing them. So, the code symbols are, I will put down P4, P5 and P6. So, there are these three symbols, and the way the Hamming code is going to impose the requirement that in any circle the parity must be even. Okay. So, for example, let us say you arbitrarily chose the message symbols M0, M1, M2 and M3, then the parity symbols must be chosen in such a way that if in every circle you actually have even parity. So, in particular that means that the following equations must be satisfied, namely that M0 plus M1 plus M2 plus P4 equals 0, M0 plus M2 plus M3 plus P5 equals 0, M0 plus M1 plus M3 plus P6 is equal to 0. Okay. So, for each of the circles you actually write down a parity check equation. So, now you can see why I called the first example a single parity check code, because there was just a single parity check that had to be satisfied there, whereas here you actually have to satisfy 3 parity checks, one corresponding to each circle. All right. Now, of course, the question is how is it that this code corrects errors, etc., but we will come back to that a little bit later. Right now I am just giving you an example of a code in terms of just saying how is it constructed. All right. So, let us now look at the code parameters. So, 1, the size of the code is, well, the size of the code, as I told you earlier, is 16, because you are free to pick the message symbols, and then after that the parity symbols are all fixed. So, the size of the code is 2 to the 4, which is 16, and as a consequence of this the rate of the code is the log of this to base 2 divided by 7. So, the rate of the code is therefore 4 by 7. The third parameter is the minimum distance of the code. What is the minimum distance of the code? So, the minimum distance really is asking the question, let us assume that someone has put down a certain set of symbols. Okay. So, let me take a particular example, I will put it down in red. So, let us say for example that I chose the message symbols to be 1, 0, 1 and 1. See, the message symbols can be chosen arbitrarily. So, let us just assume that in a particular instance they are. I am going to make this a little bit thicker so that you can see these clearer in a more clear way. So, let us say that again that this is 1, this is 0, this is 1 and this is 0, and these are your choices of the message symbols. Now, you must make sure that the parity is satisfied in each of these, and as a result, for example, what you will do is you are forced to make this equal to 0, okay, and here you are forced to make this equal to 1 and here 0. Okay. So, you pick the 4 message symbols and the parity symbols are determined after that. Now, the question is, so that gives, this is an example, this 7 tuple is an example of a code word in the Hamming code. The question with regard to minimum distance is, what is the minimum distance between a pair of code words, or asked a different way, how many symbols must I flip at a minimum in a code word to get a second code word? And let us try it with this code word, for instance. So, the question is, how many of these symbols can I flip and still get a code word? Now, let us consider the various possibilities. For example, I might flip this symbol in the center here, but if I flip this symbol, now it is a part of 3 circles. So, it is clear that if I flip this, then I have to flip at least one other symbol. Let us say that I flip this, okay, because I have to make sure that parity in all 3 circles is set. So, if I change this to a 0, all right, then I might try to balance out the parity in both of these by changing this to a 1. But then I still have to do something about this circle, and since I do not want to interfere with what is happening here, I am forced to flip this. Okay. So, you saw that in this particular instance you had to flip at least 3 symbols before you went from one code word to another. Alright. So, once again let me just repeat. So, for example, if I tried let me try picking a slightly different color and see if we can show you this. So, if I tried, let us say, changing this to a 0 and trying to make sure that parity here was balanced by making that a 1, alright. So, now I have balanced parity in both of these circles, but then I am left with this circle. I do not want to change this or this because that will upset the parity in the 2 circles that I have already balanced. So, I try to change this one. So, I do this. So, you see that I was forced to put 3 green entries here, which meant that 3 symbols had to be changed. That is an indication that the minimum distance of the code is actually 3. Now, that is not a complete proof, but I will let you complete the proof on your own. There are other ways of showing it later on. So, we will just put down here for now that the minimum distance of the code is 3. And I will leave this as an exercise for you to prove that no matter what your starting code word was, that you can never change from one code word to another by just changing 3 symbols. Okay. So, that is an important point, because here what we did was you took a particular code word and saw how many symbols we had to flip to get another one. But of course, to prove this you have to show that no matter what code word you started out with, that you would be in the same situation no matter what you did. And also there were other choices available to us, but no matter which situation you consider, you will always end up with this. Okay. So, the minimum distance of the code is 3. So, now we have actually finished looking at some example codes, but of course, the burning question is, okay, that is fine. So, you told us what a code is, you have told us what some parameters of the code are, but what I would really like to know is how do you use these codes for actually correcting errors, all right. So, for that we are going to need some definitions. So, let me get to that. A T sub C, T sub D code is a code in which any combination of less than or equal to T sub C errors can be detected and corrected and any combination of T errors where T is greater than T sub C, less than or equal to T sub D, can be detected as an uncorrectable error. This automatically implies that T sub D is always greater than or equal to T sub C in any code. So perhaps let me just in the pair we always assume that T sub d is greater than or equal to T sub c. Okay. So that is fine, but still the question is, well, how do these codes correct errors? And we will actually, the next theorem will make this clear, because what we will do is we will tie in the minimum distance of a code which we have been able to compute to these parameters T sub c and T sub d. So here is our first theorem. A binary block code C is a T sub c T sub d code if and only if the following is satisfied, namely that the d min of the code is greater than or equal to T sub c plus T sub d plus 1. Okay. So, only if this condition is satisfied is a code, a T sub c T sub d code. So, how do you prove this? So, what we will actually do is we will provide by the way, this is if and only if. Okay. So, that means that we have to show two things. One is that if this equation is satisfied, then in fact the code can be used to correct T sub c errors and detect T sub d errors. Okay. On the other hand, to show only if, we have to show that if this condition is violated, then it is not possible. And to show the if part, we will actually do this by exhibiting a very simple algorithm. All right. So, here proof. So, this will be for the if part. So, here assume that d min is greater than or equal to T sub c plus D sub d plus 1. We will adopt the following decoding algorithm. So, I am going to draw a picture that goes along with what I am going to describe. So, in the picture, this is an abstract depiction of the set of all n tuples, and here let us say that you have the received vector y. Okay. And so, what we are going to do is we are going to draw, we are going to consider in the neighborhood of this vector a ball of radius t sub c. And if there is a code word in this ball, so let us say that there is a code word in this ball which is located here, let us say, then we will declare that x was the transmitted code word. If there is no ball, if there is no code word in this ball, then we will actually say that the number of errors exceeded t sub c, and we will detect an uncorrectable error. Okay. So let me just write some of that down. Let y be the received vector. Okay. And now for any vector a in f2 to the n, let us define B of A R to be the set of all vectors of the form, let us call that Z, Z belonging to f2 to the n, such that the Hamming distance between A, so A is a vector, and Z is less than or equal to R. Okay, so this is a general definition. So for given any vector A, we can define this a ball like this. So when I was earlier talking here about a ball, I was referring to one such ball, except that here it is going to be centered around y. So our decoding algorithm will say, let us look at the ball of radius t sub c centered at y and look to see if there is a code word in there. So let me write that down. If B sub y t sub c contains a code word x, then we will declare x to be the transmitted code word. If not, we will declare that an uncorrectable number of errors have occurred. So that is our algorithm. Okay. Let me just do one thing here, since this dotted line is not so clear. Let me try to draw a circle in perhaps a different color here. So, this is the same circle that I was talking about last time. All right. So, this is your received vector. You are going to look in this ball and look to see if there is a code word in this ball. Now, often students at this point say, sir, that may be true, but what you haven't explained to us is what will happen if there is more than one code word in this ball. And what I want to point out is that it is not possible for more than one code word to belong to this ball. Okay, why is that? Because, so let me just draw that, so we will make that note. So, it is not possible for B y t sub c to contain more than one code word. And the reason being, so let me draw this circle again here. So, let us say that there were two code words whose distances were let us say that their distances were d1 and d2. Okay. So, now within this ball let us say that there are two code words and that both of them belong to the code. Then what you would have is that the distance between these two code words, the two code words themselves, let us call this distance d. Then what that would imply is that the distance between these two code words by the triangle inequality is less than or equal to the sum of these distances, which means that it is less than or equal to d1 plus d2. Okay. So, if the Hamming distance between y and x1 is less than or equal to t sub c, and the Hamming distance between y and x sub 2 is less than t sub c, this would imply by the triangle inequality that the Hamming distance between x1 and x2 is less than or equal to 2 times t sub d c, but this is less than or equal to t sub c plus t sub d, which is strictly less than t sub c plus t sub d plus 1. So, that is a contradiction. Okay. So, what that means is that we have ruled out the possibility that the ball of radius t sub c around y can contain more than one code word. So, the only possibilities therefore are that either the ball contains no code word, okay, so we are back here, either this ball does not contain a code word or it contains exactly one. Now, let us, so what I would like to claim is that the algorithm does what it promises, that is, if the number of errors is less than or equal to t sub c, it will give you back the correct code word, and if the number of errors is greater than t sub c but less than or equal to t sub d, then it will tell you, okay, there is an error but I cannot correct it. Okay. Now let's say for instance that let me just clean this up a little bit. So let's say that in a particular instance there was a code word and you decode it to that code word. So the question is, how could you go wrong? You could only go wrong if there was some other code word that was transmitted, okay. And so let's say that there was some other code word that was transmitted, which is, let's say, let's call that other code word, let's put it in a different color. Let's say, let me see if yellow shows up on your screen here. Let's say that I'll call this, I guess, okay, yellow is not a good choice. So let me try a different color. Let's go with our red. So let's say that there was another code word here which is, let's put X with a wiggle on it. That this, let's assume that this was actually the transmitted code word, but then you found another code word within this ball. Now we know that this cannot belong inside the ball, so perhaps what actually happened is that perhaps this was the transmitted code word and that this was received with the number of errors being less than or equal to T sub d. So maybe that has happened, in which case you would be in error, because what you should have done was you should have detected that there was an error which was uncorrectable. And as this figure shows, we have already agreed that x prime cannot belong in this ball. So the distance must be less than or equal to T sub c d, but greater than T sub c. So in this case what you should have done was you should have declared an uncorrectable error. Instead what you did was you declared x to be the actual transmitted code word, which means you made a mistake when you shouldn't have. But that is assuming this picture is true, but this picture really cannot be true, because if you look at this here, you cannot have a pair of code words x and x tilde which with this set of distances, and I will explain that. Okay. So once again, but before I do that, let's just to summarize that we are in a situation where the vector y has been received and you have declared x to be the transmitted code word. So the only question is, could you have gone wrong? Now if x itself was the transmitted code word, then there is no problem, and we know that whatever, if x was not the transmitted code word, the transmitted code word must be somewhere in this space, and we are only interested in the situations when the distance from the transmitted code word is less than or equal to T sub d. Okay, why is that? Because all that your algorithm is promising is that it is saying that if the number of errors is less than or equal to T sub c, then I will correctly correct the errors, but if it is greater than that but less than or equal to T sub d, I will declare an uncorrectable error. What happens beyond that? There are no promises, there are no guarantees. If the number of errors is greater than T sub d, then you just throw up your hands and give up, and that is perfectly fine, because you are not promising anything in that regime, right. So for that reason, when we are trying to actually figure out the performance of the code, we only need to consider these two cases: the case when the transmitted code word is within this ball, which we have shown cannot happen, or the case when it is outside the ball but at a distance less than or equal to T sub d. And the question is, could this happen? And as we will see, for the same reason, because of the triangle inequality, even that can't actually happen. So here is your received vector, and our concern is that on the one hand there is one code word here, whereas the true code word is over here, and the distances that you have are that this was less than or equal to t sub c, and this distance was less than or equal to t sub d. But again, by the triangle inequality, that would imply that the distance d between x and x tilde would be dh of x tilde would then be less than or equal to t sub c plus t sub d, would be less than or equal to t sub c plus t sub d, which would be strictly less, which would be strictly less than t sub c plus t sub d plus 1, which is again a contradiction, because which is okay, thank you, which is the minimum distance of the chord. So what we have shown is that you will not have an error even in this case, because even this situation cannot occur. So what we have shown is that if there is a code word within that ball, you are not going to make an error. Now what we need to actually come back and show is that what if there is no code word in that ball, then what you are supposed to do is you are supposed to declare an uncorrectable error, and what we will do in the next class is we will actually show that in that case if you do declare an uncorrectable error, then in fact that is exactly what has happened, provided the number of errors is not greater than or equal to t sub d. Okay. So I think that this may be a good place to actually stop. So just to quickly recap, what we have done in this lecture is we have looked at 3 example codes: the repetition code, the single parity check code, and the Hamming code, and we have looked at their parameters. Then I actually explain, so now we are in the process of making the connection, the important connection between the code parameters and the error correction capability of the code, and that is captured in this theorem, and we are in the middle of proving the theorem. We are almost done. We should be able to do that, wrap that up in the first part of the next lecture. Alright, so let me stop here and I will catch up with you all in your next lecture. Thank you.